Okay, this is 2022 AP Physics C Mechanics number 3, and this is in set 2. So this problem looks kind of scary. I'm going to raise the document count up so I can get more of the problem in the screen. And that should work. Okay. Alright, so in this it tells me a uniform board. Okay, so that's kind of important. Of length L and mass M is attached to a pivot L/4 from the end of the board. The left end of the board is attached to an ideal spring, so that tells me that Hooke's law, so F is equal to Kx, or F is equal to negative Kx if you want to put the negative on there, but we know that that's the force of the spring. F spring constant K is attached to the ground. The right end of the board is initially held by the student up, so the spring is unstretched. The student slowly lowers the board and then releases it. The board remains at rest in the horizontal position, so we're in equilibrium right here with the spring stretched. The rotational inertia of the board around the pivot is I. The first thing that asks us to do is on the rectangle below, which represents the board, draw and label the forces, not components, that act on the board while the board spring system is in equilibrium. Each force should be represented by an arrow that starts on, points away from the board, and should represent the location in which that force acts. So, as I always tell my students, the first force that we always think of that acts on everything is, of course, gravity. And since this board is uniform, gravity acts right in the middle. So there's the gravity of the board. Okay? But we have a spring down here. And so this board has went down, so the spring is stretched, so the spring must be pulling down. So we have the force of the spring over here on this end. Now there's two downs, so we're not falling down, so we got to have an up somewhere. It's attached to this pivot point, and that's located right here, L/4. So they've divided this board up into 4 pieces, so it's right here at L/4 from the end. So we'll push that up, and that's the force of the pivot. And those are the 3 forces that are acting on this board. Okay. Moving on. And I'm going to put this behind it so we can see our picture of our board a little bit there. It says derive an expression for the distance the spring stretches when the board is in equilibrium. So I'm going to draw that picture again. Here's our pivot. Here's our spring. And here's gravity. Okay, and they want an expression for the distance the spring stretches. The board's in equilibrium, so everything is balanced. So that means F net is 0, which means the ups equal the downs. So okay, gravity and the spring equal the pivot, but that's not going to help me because the pivot point, or the pivot force, is not in my list of acceptable things that I can do, because I can only use that and G. So then I go, well, what else is equilibrium? Well, net torque is equilibrium. So that means the things that are torquing it clockwise are equal to the things that are torquing it counterclockwise. And that's how we're going to go about solving this problem. So, what do I have? Well, if I set this as my axis of rotation, because remember I can put that anywhere, but I don't like that pivot force, so I'm going to put it there, even though that is the natural place to put it. I mean, that's the obvious place to put it, but you can put it anywhere you want to. If you wanted to find the force of the pivot, you could put it down here on the spring. But I'm going to put it there. So this force is wanting to torque this way, and this force is wanting to torque this way. So that means the torque of the spring has to equal the torque of gravity. Now, that's absolute value, so you could put absolute values on here because one of these is positive, one's negative, but we want them to be the exact same, so we're going to do them this way. The torque of the spring, every torque, we're going to do our little vector product thing here. And so R is how far it is from the axis of rotation. This is L/4. So this one is L/4. This is in equilibrium. So my spring force is K times delta X times the sine of, here's my R, here's my F, so it's going to be 90 degrees because it's the angle between this and this, which is 90 degrees. The torque of gravity is how far gravity is. Well, gravity acts right in the center of the board. So if this is L over 4, this acts at L over 2, so the distance left is L over 4. The force of gravity is mg, and it's also at sine 90 because it is perpendicular to the board and therefore the radius. So sine 90 is 1, so I can go ahead and take those out. I've got L over 4 on both sides, so why not go ahead and get rid of that. And then we're solving for delta x. So delta x is going to be mg over k. And that's going to be my delta x for this. Okay. Let's move on a little bit more. So now the student does something different. They push a little bit farther and they extend that board on up. And they want to know what's going to happen to the angular acceleration. And we want to go from time 0 to t1. They want to know what happens to the angular acceleration during that time. And so we're going to do this. I'm going to kind of, we're going to look at it through torque in the same way that we did before. Because here's our board. And there's our pivot point. So we've got gravity here. And we've got the spring force here. Okay, so these two are opposite one another. And torque net is equal to I alpha. Now I'm really kind of getting ahead a little bit into what I'm going to see next in this problem, but I want you to think about it along these lines. So alpha is going to be torque net over I. And what is torque net? Well, that would be the torque of the spring minus the torque of gravity over I. All right, now that's what it's going to be. Okay, so we can see that. But what's going to happen to these torques? Well, the torque of the spring will be L over 4 times the force of the spring, which will be K, and we're going to say X at the moment because that's going to change, and that's also going to change the angle. So I'm just going to put that in there. But this angle is going to change because right now this angle is one thing, but as I start dropping down, that angle is going to get different. It's going to get smaller and smaller and smaller. So we're going to head down to, we're going to vary with this and with this. And because we vary with those two things, it's not a linear relationship, so we're going to start with our acceleration in the beginning. This is the biggest it's going to be, the spring force is. Gravity's torque is going to change based on the angle, but not based on anything else, just on the angle. So as we shift that, our torque of our spring will get smaller and smaller and smaller. So we start at the beginning with a big acceleration. But eventually when we get down to flat, our net torque would be 0. So that means our alpha would be 0. So we're going to end up down here. But because this is not a linear relationship, we're going to have that exponential decrease in our acceleration. Okay, moving on. Now, this is where I said I was getting a little ahead of myself. It says derive an expression for the angular acceleration of the board immediately after it's released. So here's my board. This is my angle theta. This is my force of my spring. This is my force of gravity. So we know that net torque equals I alpha. We just started this a second ago. The torque of the spring is going to be greater minus the torque of gravity is equal to I alpha. So we want the initial, so we're going to go with what's happening as I just release it. Well, the spring acts at L/4 times the force of the spring, which would be K delta x2, because that's what we're stretched to. Now this, the sign. Okay, this is a little bit different. Let me grab a colored pen here so that we can see what we're talking about. So as we're doing this, this would be my R. This is my F. So this is the angle between them. Now because this is the angle that we're inclined at, then as I shift this up, this would be theta, right? And so the angle between these two, when we put the sine of the angle in there, so let's make sure I'm reading this right. Yes, okay, that's theta, which makes this theta. So this is going to be the sine of 90 plus theta. So that's going to be my angle that's in there. Minus the torque of gravity, which is L/4, times gravity, which is mg, times the sine of, also, here's gravity, here's my R, the angle between them is going to be, let's see, if this is theta, then that's going to be 90 minus theta. In 1 second while I click here, because I thought that I had squared that just a second ago. Yeah. (90 minus theta) is equal to I alpha naught. And so alpha naught is going to equal to, and we're going to just divide through by I, so I'm going to factor out L/4 I times K delta x2 sine of 90 plus theta minus mg sine of 90 minus theta. Okay, and this is our last part, part D. It says now we're going to put two blocks there of equal mass, equal distances from the pivot point. The board is again pushed down on the right side of the spring, stretches the same distance, and the board is released. How does the new angular acceleration compare with the other? Okay, well, I've got my equation right here, okay, that I was building for my alpha naught there. And one thing I know, since the blocks are equal mass and equal distance from the axis of rotation, their torques cancel each other. So net torque stays the same. But the added masses increase the moment of inertia. Because we've added some mass in there, so we're going to increase the moment of inertia. And what did this depend on? if the torque is the same, here's all the torque, what do? We divided by inertia. So if we divide by a bigger number, my alpha will get smaller. So we divide by a larger I, so alpha decreases. And that's it.